True or false? A significant result proves something is really happening. Let's look at a picture that might help. So here was our distribution from the null world. This was in our polling example, and we were considering what are all the different things that might happen if we repeated our poll again and again in the world where Melvin's support among the public is really 60%. And we have this shaded region that encapsulates 95% of our, the possibilities here. So what do you think? Well, if the null hypothesis is true, that means that because we shaded the middle 95% of the time, there's still 5% left over. And so we've got those highlighted in these arrows outside the shaded range. And so that means that 5% of the time, we're going to see results that fall outside of the shaded range. And what would we do with those? We're going to call those significant. So that means that 5% of the time, we're going to conclude that something changed, something significant happened when it really didn't. And that's sort of by design, right? Because if we said we're going to take the middle 95% and we're going to treat that as ordinary, that means that 5% of the time we're choosing, to accept the possibility that we're going to incorrectly say, something significant is happening and interesting and not compatible with the null hypothesis. And we call these a false positives, right? So this is when we say that something interesting is happening, something not compatible with the null hypothesis, when in fact it really is part of the null distribution. It is compatible. So one way to reduce the number of these false positives is to set a stricter threshold for significance. So what would that look like? Perhaps instead of choosing the middle 95% as our compatible range with the null hypothesis, we could expand it and we could take the middle 99%. Now only 1% of the distribution is in the significant range. That means that we expect false positives 1% of the time. So why don't we do this all the time? I mean, lowering our false positive rate is great, right? So if we looked at our, polling example, under this new and stricter threshold, our 70% result would no longer be considered significant. And maybe that's okay with us, but this higher threshold means that we need to see more extreme deviations from 60% in order to reach significance. And that might also be undesirable in some ways. So it's a trade-off, right? If we make it a more conservative threshold so that we're going to get fewer false positives, it is going to be harder to reach significance. So there's really no way around that. Now, different scientific fields may have different thresholds based on how important it is to minimize false positives. So in psychology, for example, it's very common to use the 95% compatibility range, and that's equivalent to having a 5% false positive rate. So you can expect that if you conduct 100 psychology studies, if using the standard thresholds, we would expect about 5% of them by default to have, false positive results. In particle physics, though, the community has entirely, together chosen to go to a stricter threshold of significance to minimize false positives. And that's because of discovering new particles, discovering, in quotes here, discovering fake particles 5% of the time is a huge drain on everybody's resources and attention. So they have a much stricter, threshold. So to go back to our true or false question, I want to ask a sort of mirror of our original question. Does a non-significant result prove that nothing is happening? If our test comes back, entirely compatible with the null hypothesis, does that mean that nothing is happening? Okay, let's look. Here's a thought experiment. I have a noisy scale. The scale is accurate within about a gram, meaning that it's usually going to display results that are at most 1 gram more or less than the true weight of an object. So here, let's say that I take my scale and I am going to place a scoop of rice on this scale. What if I weigh this rice hundreds and hundreds of times? Okay, so if I do this, I'm going to get a distribution. Most of the time, it's going to be around 38 grams, but we've got some spread here. It's not exact. And most of the time, we're going to be in this range here from 37 to 39. That's the middle 95% of the distribution. And now I'm going to add one single grain of rice, and I'm going to weigh it again. Okay, after adding the grain of rice, the scale says that we've got 38.3 grams here. And we put that on our distribution of how much this rice ball weighed before we added the single grain. And there it is. Okay, it's right in our shaded region of what we expect just, from weighing this before we added the grain. So if we were to run a hypothesis test and check, did this new grain of rice change the weight of the original rice ball? Is it significantly different from before we added the rice? Ugh, no, it's not going to be, right? We look at this, we've got these two hypotheses, and we're still entirely compatible with the null hypothesis. And because I know you haven't seen an example before where we have not enough evidence to rule out the null, we don't say something like we've proven the null hypothesis. We say that we don't have enough evidence to rule out the null hypothesis. So we're going to continue probably in our lives as if this is true. We don't have enough evidence that, the grain of rice is contributing to the weight of the pile. So that means there's no evidence that the grain of rice weighs anything, right? No, of course that's really silly. We have a lifetime of experience with grain of rices. So why doesn't this work? What is going on here? The built-in noise of the scale is simply too large to detect small changes, right? That little grain of rice is it's simply too small compared to how much noise the scale has just as a property of being a fairly noisy scale. This tool is underpowered to detect what it is we're trying to study, the grain of rice. And because we have, years and years of studies of matter in physics, we should be pretty sure that the grain of rice does weigh something, right? It's much more likely that, our tool is underpowered than that we've discovered a grain of rice that entirely breaks physics. So the tool is simply underpowered to detect what we're trying to study. That's a word that we might use here. Things that might be underpowered outside of our thought experiment. A survey with a small number of participants, right? So if you've only got a couple people in your poll, it might be very hard to detect subtle changes that are happening, in the broader population, right? Because when you have a small number of participants, it's not a very reliable sample. If I have 5 people that I pick once versus 5 people that I pick a different way, they're not always going to come out, with the same poll responses or survey responses. Another example might be a clinical trial of a drug with too few patients. If you have a very modest effect of the drug and you don't have a lot of people in the study, it's simply too noisy often to pick up that the medication helped. Another example might be a questionnaire that people tend to answer very differently from day to day. And so if you only have, you measure people twice, day 1 and day 5, but the questionnaire itself is just a bit inconsistent, it might be very hard to detect if anything else changed about their lives in that time. So not significant results, we have to be careful because if the effect that we're studying, the weight added by a grain of rice in our example, is small relative to the built-in noise of our tools, like how much the scale varies from use to use just by chance, we should expect a lot of not significant results. That's actually quite ordinary. So to recap, sometimes we find significance when nothing interesting is happening, and we should actually expect that. We should expect some false positive rate based on, how we set our thresholds for significance. And sometimes we will also fail to detect things by significance testing, particularly if our tools are noisy or when we're studying subtle things.